Buenos dias. I am Noah Walgren. Caleb Hill, Jack Ferrer, and I have been studying the heat transport in nuclear reactions. We have been researching more how these transport really affect nuclear reactors and how they might be enhanced or changed. The specific topic I will talk about and I researched was nanofluids in these nuclear reactions. And the paper that I studied was Nanofluid Heat Transfer Enhancement for Nuclear Reactor Applications. It was written by a couple of MIT nuclear scientists named Jacopo Borgiorno and Lin-Wen Hu, and it was published in December of 2009. So barely making the cut there. Now, you might be wondering what a nanofluid is. It's not just a very small volume of fluid. It is actually nanoparticles within a fluid. And so pretty much what happens is you synthesize your nanoparticles and you're able to mix them up into your base fluid, which is commonly water. And after a few other steps, you are left with a stable nanofluid. So these nanofluids are very good. They are a fluid with superior heat removal capabilities. This means that your reactor can be run at much higher power reactor rates. Now, these reactors, as you can see in this diagram here on the right, these reactors and these nuclear reactions, fission reactions, generate a ton of heat. This heat heats up a bunch of this water, generating steam, which then turns a turbine, which is connected to a generator, making a bunch of electricity. However, all this heat needs to be cooled down. Commonly, water has been used and is still used today. That's why you'll see a lot of these giant cooling towers and these reactors and these plants next to some body of water, like a reservoir, an ocean, or a lake. However, we can see, and we'll be able to tell by the end of this presentation, this short little presentation, that there are other ways besides just plain old water to keep a reactor nice and cool. However, we need to understand what happens if we don't cool them down. And so that's where we get into our limits of power production. We can't just amp up these nuclear reactions as high as they'll go, because you could have a potential of this happening, a nuclear meltdown, which is no good. So this happens as a critical heat flux is too high. Your nuclear fuel overheats and it can damage the fuel and the reactor itself. So one problem is this critical heat flux is pretty much set, and we need to be able to change that or increase that. The other limit we have is the quenching heat transfer. Much like this blacksmith is quenching his horseshoe over here to be able to cool it down rapidly, the emergency core cooling system injects cool water to the core, the nuclear core, to be able to cool it down quickly and efficiently and safely in case it gets too hot. Now, if this doesn't happen, of course, we get a meltdown. Now, what we want is to be able to run the power plant much higher than it is to be able to generate more electricity and be more efficient. So we need to increase the CHF, and we need to increase the quenching rate, or the ability to take that heat from our core and dissipate it somewhere else, right? This is where our nanofluids generate an answer. Now, our professors were able to study a lot on this. And the first figure, the first data that we'll be able to look at is right here in figure 2. This examines the CHF flow versus a mass flux, right? Now, at different and higher mass fluxes and at higher concentrations of nanoparticles in our base fluid, we're able to see a great increase right here, a great increase in CHF. So this means that we're able to run our power plant higher. It means that it's able to get that heat out much better. The nanofluid, however, excuse me, this nanofluid concentration, the nanoparticle concentration in base fluid is not so substantial. You can see in our triangle here, which is a great increase from our base CHF line right here, is only at a 1% volume percent aluminum oxide, which is our nanoparticle to water. Very small nanoparticles, which are very inefficient, are very efficient to make, very low cost to make. So this answers part of the question about the CHF. Now moving on to increasing our quench rate, we should move over to their first study over here, which was with a 10 millimeter diameter steel sphere, which they heated up to around 1,000 degrees Celsius and then quenched it. Now for a control, they put it in water. You can see this little dotted line through here, that's their water. And then they were able to put it in and quench it in other nanofluids. As they did so, and as they continued to quench it, you could see a rapid decrease in the amount of time it took to bring that core temperature down. Now, spheres are good. However, most of the fuel for nuclear reactors are cylindrical in shape. So they decided to test this theory as well with cylinders. They tested this was first in pure water, and this was in a nanofluid. So in your pure water, you can see, and at time equals 0, your cylinder is still piping hot. However, as it continues to move on, you can see this quench front slowly moving up the cylinder. That means it's cooling down. So it's partially cool, getting more cool, mostly cool, and pretty much all the way cool here. The interesting thing is that you'll see in your nanofluid, quenching it in nanofluid yields the same results. However, in a much smaller, much quicker amount of time. This took about 5 seconds, and this took about 1.5 seconds. So now the nanofluids were able to increase our CHF, increase that limit, and also increase the quenching rate, which means we're able to cool down our reactor much faster. As these nanofluids are brought into nuclear reactors, they're able to greatly increase the power production and greatly increase the electricity production for many people living around it. Our next topic will be presented by Jack Ferrer, increasing our understanding of heat transfer in nuclear reactions.
My name is Jack, and the paper that I'm going to present today shows the effects of heat transfer in regards to nanofluids versus water in nuclear reactors with dual-cooled annular fuel using computational fluid dynamics. So just to show what an annular system looks like, here in the figure below, you can see on the left, it shows a solid fuel rod system. It's just a big cylindrical cluster of fuel rods, and coolant flows through on the outer surface. However, on the right shows the annular system. So fuel rods are positioned in a circular cylindrical system, and then coolant flows through the central portion as well as the outside. So for this paper, it just starts out by mentioning some of the problems of an annular heat reactor. So the main two are asymmetrical temperature distribution throughout the fuel. So usually the center is a little bit hotter. However, the second problem is difficulty cooling the outside surface, since due to the fuel rods being packed so close together, the heat transfer coefficient is decreased for this boundary. However, nanofluids can help solve both of these problems. Nanofluids are basically fluids with suspended nanoparticles in the solution. So nanoparticles are just, well, small particles with a diameter of usually 1 to 100 nanometers. And usually these nanoparticles have very high thermal conductivities in comparison to the fluid. So when added to the fluid, you get a nanofluid that has better cooling properties or heating. But for this article, we're focusing on being able to cool a reactor more efficiently. So the goal is to model the heat transfer through the fuel as well as the coolant, using nanofluid instead of water as a coolant for the reactor. This uses alumina suspended in water, and also CFD here, as mentioned earlier, is the main modeling program used. So for the materials and methods, there's two main challenges that they have here. The first one is to find an annular system, because the reactor that they're basing this off is a solid hexagonal configuration. So it's just one solid cylinder of fuel rods. However, that's not the system we're modeling. So what they do is that they convert it to an annular system using CFD programs. And here's one of the figures of them doing that. So it starts out with a hexagonal structure. They create a lattice structure of cells that I believe this is based off a field of temperatures, and it simplifies eventually to this annular circular system here shown on the right of the figure. It's also labeled for coolant, fuel, and cladding. So cladding basically surrounds the fuel and keeps it away from the coolant. And the second challenge was modeling this flow and thermal properties. So there was a lot of properties such as mass density, specific heat, viscosity, and more that they have to either input as a parameter or solve for using all of these different equations. They also use mass, energy, and momentum balances solved with Fluent, which is a program they use for calculating all of this. And this also it shows here on the right figure that it just basically shows that they're on the right track. And how would they do this is that they show a modeling system for two other research articles shown in blue and orange. This paper's modeling calculations are in green. And all it does is that it shows that the average coolant temperature for water for their modeling system matches the other researchers, just showing that they have very similar values and that they're not just going against the mold here for their calculations. Now for the results, they have a lot of good ones, so I'm just going to highlight the main results. Now, first of all, this shows the outer and inner temperatures of the clad, so basically surrounding the fuel rods. And as you can see here, water is the top curve, and the ones below it are all with nanofluid, showing that nanofluid being used instead of water does lower the temperature of the fuel rods in clad as a result. This is due to thermal conductivity being increased using the nanofluid, and they show this partially through the equation below, which is a thermal conductivity coefficient. It basically compares the thermal conductivity of the nanofluid versus the fluid, which is that fraction on the left, and then all those terms on the right are just used for calculation. Now, as the volume fraction or concentration of nanoparticles in the fluid increase, you can see that the temperature keeps getting lower and lower. And partially it's because these higher concentration nanofluids have a smaller particle diameter, as you see in the equation, does increase the value of that coefficient. They also show this in terms of the coolant temperature. So this is the intercoolant. As you can see, water is now the low temperature, and as the volume fraction of nanofluid increases, the heat flux as a result increases, and that raises the temperature of the coolant because it's taking that temperature or heat from the reactor core or those fuel rods. Lastly, you can see the local heat transfer coefficient on the outer coolant, which was one of the main problems. They had trouble cooling. It kept on getting decreased. However, now you can see that as you decrease the size of nanoparticles at a fixed concentration, that heat transfer coefficient now increases. So you can adjust either the concentration or the size of your nanoparticles in nanofluid, and you can fix that heat transfer coefficient problem from before. So here are my references. And then up next is the characteristics of convective heat transport in a packed bed.
Today I'm going to talk about characteristics of convective heat transport in a packed pebble bed reactor by Raymond S. Abdelmohsen and Mutana H. Al-Dahan. This paper talks about nuclear reactors and dissipating heat from a nuclear reaction. When this paper was written in 2015, packed pebble bed reactors, shown in this image here, were still emerging, and they were very promising for the dissipation of heat in nuclear reactors. So generally, how this process works, compressed cooled air is blown through the top here and through the packed bed out through the bottom. And that cooled air takes the heat from the spheres. The heat is transferred from the spheres into the air, which then goes out the vent. They used a thermocouple sensor that they put inside of a pebble, so to speak. They created this sensor that is the same size as their packed bed. It has a copper outer casing, a Teflon inner core, and then a flux sensor for heat and a heater as well. And so they created the sensor and they tested it at 3 different positions vertically. They tested near the top, the middle, and then the bottom. And then they tested at 4 positions radially. They tested at the center, third, 2/3, and then right close to the wall. And so they had 3 positions vertically and then 4 positions radially that they tested at. Overall, they were trying to find the heat transfer coefficient for this pebble bed. So in this first graph, we have the results for the center and for near the wall. These graphs are of the heat transfer coefficient on our y-axis and the superficial gas velocity, so the speed of their cooled gas coming in from the top on the x-axis. Near the center, we can see that we have a lot smaller values for the heat transfer coefficient, about 80 watts per meter squared Kelvin versus close to 110 watts per meter squared Kelvin near the wall. And we can see that near the top section, where the flow is not quite fully developed, we get smaller heat transfer coefficients than near the middle or at the bottom. Additionally, on both these graphs, here and here, we can see the difference between laminar flow and then turbulent flow out in these regions. In laminar flow, we see this sharp change in the heat transfer coefficient, and in turbulent flow, it's much more linear and much more gradual. And so these lower numbers are low Reynolds numbers, laminar flow. Higher velocity is going to be turbulent flow, high Reynolds number. We can see the different radial positions here. So we have high velocity on the left and low velocity on the right. And these are normalized, so it's 0 to 1. And then our heat transfer coefficient. Again, we can see that the high velocities are on a much greater magnitude than the low velocity heat transfer coefficients. And near the top, we see that smaller values again for the heat transfer coefficient because the flow is not quite fully developed. Heat doesn't transfer quite as well as it does in the middle and bottom sections. From these results, they determined that you can't really have a global heat transfer coefficient for these packed pebble beds. And from their paper, here's a quote. It says, "The results and findings clearly indicate that one value as an overall heat transfer coefficient cannot represent the local heat transfer coefficients within the bed. Hence, correlations that predict radial and axial profiles of the heat transfer coefficient are needed." So in class, we learned that the heat transfer coefficient is very general, very global, but their findings show that in these packed pebble bed reactors, it is much more local. And they suggest that there should be an equation of sorts for the heat transfer coefficient that is based off the axial, the vertical position, as well as the radial position.
All right. Thank you very much for listening and watching. We hope that you were able to learn much about heat transport in nuclear reactions and reactors. We would like you to know that this heat transfer is crucial not only for our nuclear reactors, but also has many applications in biological systems. Now, the nuclear reactors are most simply a very radical change, and they allow us to understand this heat transport better because the heat change is so drastic. These nanofluids and packed beds also have very big and important applications in biology. Some of nanofluids applications being heat transfer in microelectronics, fuel cells, pharmaceutical processes, hybrid powered engines, engine cooling or vehicle thermal management, domestic refrigerators, chillers, heat exchangers, grinding, machining, boiler flue gas temperature reduction. There are so many applications for that nanofluid. And for packed beds, they have many advantages. Packed beds have many advantages in bioreactors because they're able to reuse many of the enzymes and make that way of operation a lot more continuous. These packed beds are also very versatile and used in many chemical processing applications like absorption or distillation, stripping or separation processes, even catalytic reactions. So even though nuclear reactions may not necessarily be put under biology, it helps us to understand the heat transfer in a much more dynamic scale for how the same kind of heat transfer would happen in, say, a cell, pharmaceuticals, or even through packed beds and bioreactors. Again, thank you for watching, and we hope that you continue to learn.